Alright, here we are back again with some more nomenclature. We're going to start by talking about cis and trans isomers of alkenes. Just to remind you, when dealing with substituents, we have the following suffix YL in association with number of carbons coming out of the parent chain. If you have halogens, we basically take that halide ending and turn it to halo, so fluoro, chloro, bromo, iodo. Your ether linkages are alkoxes, and then you have phenyl and benzyl linkages as well. Now, in addition to all this, there is a feature in association with alkenes that needs to be mentioned at this point, and it is the fact that if we look at these molecules, in one instance, in respect to the double bond, we have alkyl chain going in one direction and going in the opposite direction on the opposite end of the alkene. So we have one going down, one going up. Whereas here we have two things going in the same directions. One goes up, the other one also goes up. Now, in terms of the naming, if you count the position of the alkene and the number of carbons altogether, you see that this is 3-hexene in both instances. The second molecule here has a 2-methyl substituent present in there, but because you have the alkyls in opposite and same size of the alkene, we have a prefix that also goes in accordance with this name. In the case where you have opposite positions for the alkyls, we call this the trans configuration. When they're in the same side, we call them the cis configuration. And so we input those things as prefixes in italics prior to the entire name. And after that, you always separate it with a hyphen. Okay, so to give you an idea, let's take a look at this example. The procedure is the same as what we've seen before. We have to locate the longest chain that does contain the functional group. So in this case, if we go from this end all the way down to this end, we find out that we have the maximum number of carbons. The other thing to notice as well is that we have the alkyls in opposite positions. One goes down and the other one goes up in respect to the double bond. So this is going to be a trans configuration. So we start with that. And now we count the number of carbons. We have 1 all the way up to 8. Since we're dealing with 8 carbons, this is the octa prefix in terms of the number of carbon atoms. And for the alkene, if we count this blue chain, the first time that we encounter the alkene is at position 4. So this is 4-octene. And in addition to that, as you can see, we have 3 methyls sticking out of the chain. So this is going to be trimethyl, right? So tri for 3 methyls, and then octene. And the octene appears at position 4. The methyls appear at positions 3, 6, and 7. All right, now that's if we go from that end. If we look at the opposite direction, if we start at this carbon and work our way towards this final carbon up here, then the alkene turns out to appear at the same position, so there's no change there. But now the methyls appear at positions 2, 3, and 6. So the alkene is unchanged by this, so there's nothing to be done there. If there was a change in the numbering, the alkene will automatically dictate which one of the number schemes you go with. But in this case, it's all up to the substituents. And simply you just compare what the numbers are from the top to the bottom in this series. And 3 going to 2, that's good. We have decreased the number. 6 going to 3 is also good. 7 going to 6 is also good. So we have 3 good ones in respect to the green one. And what that tells us is that the green scheme right here is the correct one for the name. All right, now let's take a look at cycloalkanes, because there's something interesting about these molecules. And much like the alkenes, we're also going to see this trans and cis configuration. Now, the way in which this arises is by the fact that the cycloalkane doesn't have full free rotation along its bonds. So if you do have a substituent, on top of, let's say, this triangular shape, like as shown right here with the bold bond, then that remains on the top face of this triangle. But if you have these dash bonds, this tells you that you're below the face of the triangle, and they are kind of stuck in those positions, creating this trans configuration. So one is above, one is below the plane of the cycloalkane. Whereas the cis case, either both of them are on top or both of them are at the bottom, and technically they're the same thing, as long as the groups here are the same, because you can always rotate the molecule 180 degrees on its own axis and you will yield the molecule you see here from the one that you start up there. So these are technically the same molecules. In terms of the naming, this is your 1,2 dimethyl cyclopropane structure, but this is trans because of the fact that one is above the plane, one is below the plane of the triangle. And over here you have the cis configuration. So this will be the proper naming for these molecules. Now the other thing I want to also present to you, just to get started thinking of these things, is that the 3D picture of these molecules, it's actually not too complex, but if you look at this thing, this is almost like looking at it from one of these corners, head on, and you have the back of the triangular face here. And what you see right here is that you have your methyls above or below. And the idea right here is that when you look at these bonds, if they are both, they tell you that they're coming at you. They're at the top of the face of the triangle, but at the same time, this is a cycloalkane, so you do need to have 4 bonds to complete the octet of this carbon, meaning that if this methyl group is above, the hydrogen that's still bound to that carbon needs to be below. So when you see this bold bond, the thing you have to remember is that it has to be above the hydrogen. So this methyl above the hydrogen is the one that we see here on the bold bond. And the one here that is below the hydrogen, since this is dash and below the plane of the cycloalkane, has to remain below the hydrogen. So you see the representation in 3D for this 2D picture. In a similar fashion, if you look at the cis configurations, you will have to have both of them up or both of them below the hydrogens, right? In this case, we're looking at the above and above configuration for the cis isomer. And similarly, when you look at cyclobutane, you could have trans, so one above, one below, or both of them above, both of them below for the cis configuration. And in terms of the naming, in this case, we have the 1,3 dimethyl cyclobutane structure. We have the trans, as shown here on the left, or we have the cis, as shown here on the right side of the screen. Now for the trans configuration, what's interesting about the cyclobutane structures is that now you can somewhat create a structure that is not exactly linear. Now it kind of creates this envelope-like form, and regardless of that complexity, the one thing that remains true is that if this bond is bold, this R group, this alkyl group, has to remain above the hydrogen. And if it's dash, it has to remain below the hydrogen. And that's what we see right here. The methyl is above the hydrogen, whereas right here the methyl group is below the hydrogen, as depicted in this diagram. Looking at the cis configuration, same idea. If you are dealing with the bold bonds, both on the same side, then both methyls have to remain above the hydrogens, and that's very crucial to get right when going from the 2D structure to the 3D structure. All right, now let's take a quick look at the 5-member ring cycloalkane. So this is cyclopentane, and in this particular structure we have the 1,3 configuration for the dimethyls. So this is 1,3 dimethyl cyclopentane. In the case where one is below and one is above the plane of the ring, this is the trans configuration. If both are on the same side, and this is the cis configuration. Now to take a closer look at the trans configuration, the 3D structure is a little bit more interesting. This is what we call the half envelope structure. And this is where you break a little bit of the planarity of the polygon so as to accommodate the bond angle to be as close as possible to that 109.5 degrees associated with the tetrahedral carbon. Now, in any case, you're going to have a bond that points up and you're going to have a bond that points down for every single carbon of this cyclopentane. And so when you're looking at your structures, you just have to ensure that you are placing the methyl groups or whatever alkyl groups you have above or below the hydrogen, depending upon what kind of bond you have. So in this case, the bond is above, so you have to place the methyl group above the hydrogen. And then the next one, if you go kind of clockwise here, and you follow the same picture here going clockwise, going from this carbon to this one to that one, this being the third, In this case, the methyl group is meant to be below the hydrogen, and as you can see, the methyl group is below the hydrogen. Now, another thing to point out here is that since we're breaking planarity a little bit, we have to ensure that when we draw these external bonds, they are drawn in such a way that you still retain that tetrahedral-like structure. And that's the whole idea behind it. In fact, by the time we get to, yes, and there you go, above hydrogen, below hydrogen. By the time we get to the hexagonal structure, that's going to play a huge role. Now, right here, once again, methyl is above the hydrogen, methyl is above the hydrogen, meaning that we're dealing with the bold methyl configurations. So just remember that bold bonds above the hydrogen, dash bonds below the hydrogen. All right, now here's where the more complex case is encountered, the cyclohexanes. In particular, this is the dimethyl 1, 2, 3, 4. So this is 1,4 dimethyl cyclohexane. And since in this case we have a bold bond and a dash bond, this is a trans configuration, whereas over here, bold and bold or dash and dash is indicative of a cis configuration. So this is how you distinguish the two of them when you look at them in 2D. But in 3D, here's where things get a little complicated. You may recall from a previous lecture that I did mention that the bond angle here is not 120 as you would predict from a regular hexagonal structure. And the reason why is because the 3D structure is actually very far from linear. This is what we call a chair configuration, because it kind of looks like a chair. Obviously you're missing the legs here, but this is a chair. If you're a little bit imaginative. Now the deal here is that you're still trying to achieve that tetrahedral arrangement on each one of the carbons. So notice that on this carbon you have a bond pointing straight down, and then you have one that's going up and to the left. Here you have a bond that's going straight up, and then you have one that's going down and to the right. And you have this nice tetrahedral structure on each one of these points. Now, if this is the trans configuration, one methyl group remains above the hydrogen, the other one remains below the hydrogen. And notice here that this methyl is above the hydrogen, whereas that one remains below the hydrogen. And this is what we constitute as being a trans configuration. The cis configuration, same idea. You have to have them on the same side, but what that really means is that if you stick with the bold bonds, both methyls have to be above the hydrogens. And what you can see right here is that this methyl is above the hydrogen, and that methyl is also above the hydrogen. Okay, so in the next video, we're going to look at a little bit more of a complex picture, a complete picture of the cyclohexane molecule. We'll look at each one of the individual carbon sites on that hexagonal framework, and we'll extend the way in which we look at the molecule just a tiny bit more. So see you in the next video.